So the next thing we're supposed to be able to do is look at either this equation right here, the given equation, or the graph and determine if it's a function or not. We can see that this one is not a function as simply as seeing that it fails the vertical line test. That's not a very good vertical line, so let me see if I can do that better. I can do that better if I insert a shape. And let's let the shape be just a line. So I'm going to insert a vertical line. So there we see I put a vertical line in there. That vertical line intersects this graph in two places. It intersects it right here and right here. So while this may be a piecewise relation, it is not a piecewise function because we have two y values at this particular x value. And there's several more too. All you got to do is just move that vertical line over a little bit. It has two x values right there, it has two x values right there, it has two x values right there. So anywhere it crosses the graph two places, it fails the vertical line test. We only need it to fail it once. So that's why they were asking you, can you connect two parts of the graph with a vertical line? If the answer is yes, then it's not a function. The reason that that's happening is because we've overlapped on our domain right here. When it says x numbers that are less than 3, we know what numbers those are. Those are, if you're thinking about a number line, it's like 2.5, 2.6, 2.7, 2.8, 2.9. And then we get to 3, okay? Numbers that are bigger than 2 are 2.5, 2.6, 2.7, 2.8, 2.9, 3, 3.1, and so forth. So you can see that in this list of numbers right here, I have a whole bunch of overlaps. That's why it's not a function. Most of the time, these two numbers right here, the endpoints of the pieces, those are going to be the same number as we see here. Those are going to be the same number. So when it's the same number, you don't have to worry about overlap, but you do have to worry about whether or not we have a bar in both places. Because if you can see right here, this is not going to be a function because there's a vertical line that fails the vertical line test. Now, the difference between this one not being a function and this one not being a function is that this one is not a function in several places. This one's not a function only in one place, but it doesn't matter. Well, if it fails at one time, it fails it altogether. So what would change this if either one of these didn't have a bar? If this one didn't have a bar, and that's the one with the positive slope, then this one right here would be open. If that was an open circle, we had an open circle and a closed circle that stacked on top of each other, that's okay. That would be a function. As you can see on this example right here, there is, they don't line up, but there is a gap between those two. Ooh, my line should be straight. There's a gap between those two. So there's several places where there is no y value for a few x values. So everything between 2 and 3 right here, that doesn't have a y value. They don't have y value. So there's a gap right there. So it's going to always pass the vertical line test. All of the vertical lines over here are going to only intersect this branch. All of the vertical lines over here are only going to intersect that branch. So this one is a function, even though it doesn't have the same number right there. But like I said, most of the time they do have the same number. On the end, one of them stops at the number, the other one starts at the number. And as long as one of them is open or they're both open, then it will be a function. Okay, the last thing we're going to look at is, and it doesn't matter if it's a function or not, the last thing we want to be able to do is evaluate the graph or the relation, or if it's a function, we might want to evaluate that. So here's how you evaluate. Let me clean this off real quick. You evaluate by, if you're using the equation, then you're just going to plug and chug. Okay, so here they may say find the y when x is equal to 0. Okay, so find y. They want you to find the y value when x is equal to 0. Okay, so we can see over here, well, here's where the x is 0. It's right there. And the point that we're looking at right there is going through the y-axis, so the y value is 0. So we can see right there when x is 0, the y value is 0. So when x is 0, y is 0. If you want to do it algebraically, then you would have to go up here and say, okay, so which one of these branches does the 0 fall in? In other words, is this 0 right here a number that's less than 3, or is it a number that's greater than 2? Well, 0 is a number that's less than 3. So when I plug that 0 in, I'm going to plug it into this equation right here because 0 is a number that's less than 3. So algebraically, I'm going to say 2 times 0. I'm going to calculate my y by saying 2 times 0. And that's where I calculate y to be 0. So graphically, I can see that when x is 0, y is 0. And algebraically, I can see when I plug in 0 for x, I get a value of y that's 0. So let's do another one. Let's let x equal 5. Okay, so if I let x equals 5, we'll go to 5 on the x-axis. Where do I have to go to get on my graph? There's the point, 5. And what's the y value right there? Well, the y value happens to be 5. So when x is 5, we've just found graphically that y is 5. All right, how did that work out algebraically? Graphically, you can see I went to the x-axis at 5, and then I moved until I got to an ordered pair, my graph, until I got to my graph. And then I paid attention to what the y value was at that ordered pair. Algebraically, I would start off by saying which branch, and that's what these are 2 branches, which branch does x equal 5 fit in? Is 5 a number that's less than 3, or is 5 a number that's greater than 2? And I'm looking at these two. Is 5 a number that's less than 3, or is 5 a number that's greater than 2? 5 is a number that's greater than 2, so I'm going to plug 5 in right there. And when I plug 5 in right there, I get y is equal to 5. So that's where the 5 came from. So let's jump down here and let's do another one. What if I ask you to find let x equal 2? Well, if I ask you to let x equal 2, in this case, because 2 is in both of these cases, I would have 2 answers. And that should be kind of confirmed with this one over here, because if I go over here and look graphically, when x is 2, I have a value right there. I have a value at 2, 0. I have a y value right there at 2, 1. So I have 2 answers when x equals 2. So when x equals 2, my y is going to equal 1, or my y is going to equal 0. That's happening because this one was not a function. When it has functions, I don't have 2 answers. Algebraically, what would happen is I would have to plug 2 into both of them. I'd plug 2 in right there, and then I would plug 2 in right there. So when I say 2 minus 2, well, that's where I get 0. That's how I get that one. And then if I plug in 2 right there, the negative sign, I plug in the 2, and then I do plus 3. Negative 2 plus 3, that equals positive 1. That's where I get this answer right here. So algebraically, I plug it in, and graphically, I just go to the given x value and try to find the y value. So let's do another one. Let's let x equal negative 1. So when x is negative 1, graphically, I'm going to go to where x is negative 1. There's x that's negative 1, and then there's the dot right there. So when x is negative 1, the y value is going to be 4. Okay, that's graphically how I found it. When x is -1, when x is -1, y is 4. But algebraically, how I'm going to find it? Where, which branch is -1 on? The -1, is it a number is -1 greater than 2, or is -1 less than 2? -1 is a number that's less than 2, so I'm going to plug it in right here. So I'm going to say negative, plug in the -1, plus 3, and I'm going to calculate that to get my y value. So negative, minus a -1, that's going to be a +1, and then +1 plus 3 is 4. So algebraically, I got the same answer that I got graphically.